Hi, good morning. I think that clock is behind, right? That
Yeah.
little
It's
behind.
12.
Okay, let me change it. Maybe the battery is dying.
It's only off by a little bit.
Huh?
I said it's only off by a minute or two.
Oh. So, oh, okay. Almost 4 actually. Okay, let's see. 1, 2, 3. Yeah, 4 minutes. Not too bad. You know, I don't even know which time is the real time. Is it when you fall backwards, or right now is the biological time? I mean, which one is the one that nature intended? I get so confused with those. I actually have an uncle in Mexico that refuses to change his clock, and he lives on the US Mexico border. So when he crosses into Texas, he expects the stores to keep the same hours all year long and gets angry if they're closed. He's like, well, I mean, he's just too weird. One minute. See, that's better. You can eat here. I don't feel the guilt of having food in the other one. I mean, that like I feel over there. I put a sign.
There's no one there.
No one there, right? Okay. I did put a sign on the board, so. Okay. So let me get started. To make sure that the two Monday meetings and Wednesday meetings continue to be in sync, we don't have a face-to-face meeting next week because Monday is a holiday. So I'm going to not have it either day. Otherwise, we'll be off sync. So again, I'll remind you at the end of the day, but next Wednesday there's no meeting. And of course, there'll be no new material, no new homework, nothing until we come back. So hopefully you can enjoy that time away from the classroom. Okay, so we are now in chapter 3, which is the first real chemistry chapter. I mean, I say that because we spent a lot of time in chapters 1 and 2 reviewing numbers, arithmetic, algebra even, how to solve some equations. We are still going to need those skills as we continue moving forward in this course. And in fact, in chapter 3, there's one formula that you need to be able to manipulate, but that comes later. So what are the big topics of this chapter? I like to divide it into two main subjects. One talks about matter and the most basic properties of matter. So let me put that word here. And then the second half of the chapter deals with energy. So energy is not the same thing as matter, they're related. Really interesting, you may know this equation. Maybe not, but maybe you do. I tend to lose myself in time now. As I get older and older, I lose track of, my God, I was born in the 60s, so that's a long time ago. And in the 70s and 80s and maybe even the 90s, the name Albert Einstein was known by almost everyone. Oh, you're like Einstein. That was a synonym of being smart. Today, I don't know if you guys, the younger generation, know who Einstein is. Do you? So you've heard that name. Well, this physicist came up with a lot of theories that were very interesting. But one of them is summarized by that equation. We're not going to use it for anything except that because this chapter talks about matter in the first half, and then it talks about energy in the second half, I just thought that there's a connection. This actually stands for energy. And this actually stands not for matter, but for mass. And matter has mass. So there's a relationship between matter and energy. And it's given by this. If you don't know this, the c is just the speed of light. So apparently energy and matter can be interconverted, and somehow, I don't understand the equation, but somehow the speed of light comes into place. At any rate, so that first half, matter, talks about how the universe is composed of what we can call pure substances. So we're going to divide matter into two large groups of, I guess it's a classification. Something called pure substances, and then another large group of matter known as mixtures. We'll spend a few minutes talking about pure substances, and then we'll talk also for a few minutes about mixtures. And then we're going to move on to talk about properties of matter that are either considered physical or chemical. And I'll try to make the distinction clear to you when we get to that discussion. Now, pure substances actually can be subdivided into two groups. One is going to be called the elements. And I guess the word element means basic. So this is the most basic ingredient of matter. I'm going to put in parentheses a word that is going to become, of course, important in a future chapter, atom or atoms. Now, let me backtrack just for a second because I haven't formally tell you what matter is. So matter is everything in the universe. Anything that occupies space and has mass is matter. So virtually everything. The only thing that you could say, well, that's not matter, is vacuum. Vacuum is empty space. There's nothing in it. That's the only thing that is not matter. Everything else, even the air that we're breathing, is matter. It has particles. It has ingredients, if you will. Well, the most basic ingredients of everything is the so-called atom. This is the most fundamental basic ingredient of every chemical, of every particle of matter in the universe. Keep one thing in mind. As much as we can do as humans, we cannot still do what, and I'm going to call what I believe is called God, what God can do, which is create something out of nothing. Right? There's this little joke about an arrogant scientist that says, you know what, we can actually do everything now. We can convert certain ingredients into other ingredients. So we don't need God anymore. And this arrogant person summoned God and said, okay, you can go away, God. We don't need you anymore. And actually, God appeared. This is a story, of course. And God said, okay, fine. You are right. You can do everything. But let's have a contest here. Let's make a person right now. You make a person, I make a person. And the scientist goes, sure, why not? So God goes into one part of where they were meeting and starts getting some stuff together. Let's say just dirt and water. Go back to the Bible. And starts shaping a person. And the scientist looks at God and is like, okay, I'm going to do the same, and starts getting some dirt and some water. And God goes, wait. I made that dirt. I made that water. You go ahead and make your own water and your own dirt, and then it's a fair game. But you have to make it out of nothing, out of emptiness. I mean, really, think about it. The so-called beginning of the universe, the Big Bang, happened, right? Maybe if you don't believe in God, which is fine, well, maybe the Big Bang is God. I mean, something created something out of nothing. We humans cannot. But we can transform matter. We can transform matter into many, many things. We can take the ingredients of this marker and make something else out of the ingredients of this marker. That we can do. And that is very, very cool, very huge. Now, everything, however, is composed of a very finite number of elements. By finite, I mean there's a certain total number of ingredients from which everything else is made. We're going to call those ingredients the elements, which are composed of atoms. So the two are not the same, although they are very closely related. And I'm going to try to explain them in a second to you. Now, the other kind of pure substances that we're going to talk about are called the compounds. Now, compounds are made up or made of elements. They're composed of elements. And the number of these is infinite. we can keep making new things and new things and new things, slightly different from what we made yesterday. So there is probably an infinite number of compounds, whereas there's a finite number of elements. What is that number? Well, let me just share with you the place where you find the name and, in fact, also the symbol of this finite number of elements. And that is called the periodic table of the elements. Your ebook has one. Please try to locate it. All you have to do is search for periodic table. Let me put the word over here. And we're just going to call it that, periodic table. We're not going to call it the periodic table of the elements. Too long. But here on the screen I have one of my favorite ones. It's from the National Institutes of Health. And as you can see, it's a big group of elements. Now, not all of these, by the way, are natural. Only 91, 92 of them are natural. The others are actually human-made. We made them from ingredients of other elements. So all the way to about 91, 92, these guys are all natural. The table is listing these elements not by name alphabetically, but by a number that we're going to learn in the next chapter. Is called the atomic number. So is that number right here, that number right there. And it has actually a very unique property. Let me click on that one just to bring it up and highlight. So this element, a pure substance, has a name, hydrogen. It also has a symbol, capital H. All elements have a symbol in addition to their common name. And the symbol is either one single letter, which is capitalized always, or two letters. First one capital, second one lowercase. This number is like the ID, Social Security, student ID, whatever. It's a unique number that identifies the element and no other element. So only hydrogen has the atomic number 1. Okay? Another element with a different name is going to have a different atomic number. In the next chapter, we'll learn what the atomic number tells you about that element. Now, hydrogen is made up of atoms of hydrogen. So hydrogen is an element, but it's composed of little pieces called atoms of hydrogen. Are there any other elements? Well, 90 plus natural, and let me show you number 2. So the second element in the periodic table is called helium. You may actually know what helium is because it's used to fill up some balloons so that the balloons float. They float because the helium is less dense has less density than air. And it has an atomic number of 2. A symbol He. Now, the names obviously were invented by someone, and most of these names come from when they were discovered. Somebody decided, okay, what am I going to call this element that I just discovered, and I'm going to be famous for the rest of the history of humanity? Well, hydro means what? Hydro means water, right? To hydrate means to drink water. Gen typically means generating, making. So hydrogen makes water. It's not water, but it's in water. It makes water. So that's probably how the person who discovered this element came up with the name. Here's the year when it was discovered. 1766. That's, God, over 300 years ago. Actually, that's really interesting. I live in a house that was built in 1756. So 10 years later, from when my house was built, hydrogen was discovered. Yes?
The name was derived from the Greek hydro, and genes means water in form.
Okay. So, you can sort of guess what some of these names. And thank you for that, because every one of the elements has a history as to why it was named like that. Now, some of them are more obvious than others, and you don't have to rely on Google. For instance, let's take a look at, I don't know, Californium. I don't know where that is. Let's see. If you see it, let me know. Oh, actually, that's not a natural one, but there is Californium. What does that mean? Not a trick question. Somebody who loves California named it that, or maybe it was discovered in California. Now look at this year. 1950, just 50 years ago, 60. This is made by humans. It doesn't exist in nature. So only 93 of the elements are found in nature. The others are made. Are they difficult to be made? Well, yes, they are, and they don't live for very long. They actually disintegrate in a matter of seconds. So they don't compose any compounds. As we're going to see, compounds are made up of elements. Well, these strange elements do not have anything to do with nature. They're invented by humans. Now, before we leave this periodic table, I don't want to lose my place here, so let me keep clicking. I want you to notice a couple of things, because we're going to spend an entire chapter learning about the periodic table. But as a good introduction to this very useful tool, this is more useful than any beaker, any flask, any scale, any instrument in the lab. This is a miracle of information. The table has columns, right? And you can see how orderly it is. On top of the columns, there's a number. These columns are called groups. Group 1, Group 2, so on and so forth, until Group 18. So there are 18 groups in the periodic table. And then you have rows coming across. They also have numbers. 1, 2, 3. Those rows are called period or periods. So we have groups and we have periods. So the word periodic means a pattern, a certain periodicity, if I can pronounce that. Now, why is that important? Well, because let's say that I ask you to identify the element that resides at group 2, period 3. Well, you find group 2, there it is, and then you find period 3, there it is, and the only element at that location, with that address, if you will, is magnesium. No other element has the same address. It's just like using your GPS. You want to find a restaurant, you use the GPS, it takes you to the exact location of that restaurant. This group number, period number, is a specific location for every one of the elements on the periodic table. Yes, please.
So there's 18 groups in the periodic table, correct?
Right.
And there's 7
7 periods, yes. There's actually more than 7, although
8, 9, yeah.
this is really interesting. The reason why this is down here is because they couldn't fit it here in a very nice way. So this actually can be brought up in here, inserted in here, and then you open this up. So the problem is, and I'm glad you asked that question, is that we don't really need to worry about elements beyond, let's say, 18 or maybe 20 or so. These elements over here, as important as some of them are, gold, silver, they're not part of life. And in this chemistry course, what we emphasize is the relationship between chemistry and then the biological sciences. I mean, you're learning chemistry because you are probably wanting to become some sort of a professional in an allied health field or in a forensic science or in, I don't know, dental hygiene, medical school, nursing school, etc. So we only need to concern ourselves with about 20 or so of the elements. And down here, there are elements that, quite frankly, are difficult to comprehend. They're too strange, too weird. But you're right, there are 18 groups and only 7 periods of importance to us. Now, later in the course, you're going to find out that that number is some sort of a magical number. It does mean something. And that the number of periods also means something. Not only a number, but it has something to do with the nature of the atoms. I don't want to jump ahead because it's, information that we need to process a little at a time. But it's going to tell us about something called the electrons. And the electrons are part of atoms that actually define how these guys interact with each other. Now, which elements are familiar to you? Certainly carbon, right? You've heard of carbon. This is why life is possible. Without carbon, life wouldn't exist, at least not the way we know it on planet Earth. Maybe there's another planet somewhere else where the life is based on silicon or another element. But on planet Earth, everything is based on carbon. Okay, so that's what the elements are. A finite number composed of atoms, and they are found in the periodic table. They are all pure substances. The next type of matter that we want to talk about are the compounds. Now, you are familiar with a number of compounds, and I'm going to remind you that, in fact, you do know at least 3 compounds that, well, they're everywhere. So one of them is plain old H2O. If you don't know what H2O is, I'm going to tell you right now, it's water. Okay? Now, this compound is composed of hydrogen and oxygen. Those are both elements found in the periodic table. But this is a compound because it's made up of more than 2 elements, and these 2 elements are different. Now, this is called a chemical formula, and it tells you the precise composition of water, chemically speaking. For every 1 unit of water, you have 2 units of hydrogen and 1 of oxygen. Every water unit, let's call it molecule, is going to have 2 hydrogens and 1 oxygen, no matter where the water is from. I didn't put this one on Monday that is coming up next. So I'm going to show it to you, and hopefully I'll remember and mention it to them next time we meet. But that's another molecule, another compound, different from water. I'm going to put the other 2 that we talked about. And then let me just ask you, do you guys have any idea what that is, H2O2? Anybody? Looks like water, doesn't it? I mean, H2O, H2O2. What is it? Hydrogen peroxide. Hydrogen peroxide. You were very close. You had it on the tip of your tongue. So this is actually hydrogen peroxide, the stuff that many of you probably have in your first aid kit or kitchen cabinet or what have you. Very different from water, even though the difference looks subtle, only 1 extra oxygen per unit. You cannot drink hydrogen peroxide, it's toxic. When you put it down the sink or on a cot, it bubbles. There's something going on there very interesting. But my point right here is that just that single change, adding 1 oxygen to this apparently same molecule, makes this different. In Spanish, and maybe in other languages that are Romance or related to Latin and Italian, this is actually agua, which is water, oxigenada, oxygenated. So it's oxygenated water, just as the term peroxide means. Peroxide means more oxygen. Oxygenated means more oxygen. So oxygenated water, same thing as hydrogen peroxide. But now let's talk about 2 others that you may be familiar with. You probably call CO2 CO2, right? We don't call it anything else. But some of you may actually know that that's called what? Carbon dioxide. So this is called carbon dioxide. Whereas the one at the bottom looks very similar, would be called what? What do you think? Carbon something oxide. What's the other one that is out there that is so scary? Monoxide. So carbon monoxide, it turns out that di means 2, mono means 1. Mono 1, di 2. So carbon monoxide looks like carbon dioxide, but it's 1,000 times worse. Carbon monoxide is very toxic. If you get carbon monoxide poisoning, it's very difficult to reverse. People die of carbon monoxide poisoning. It binds to your blood just like oxygen binds to the blood, and it doesn't let go. But oxygen can carry oxygen to the brain, which is needed for cellular function, and carbon monoxide does not carry any of that. So very nasty. Carbon dioxide is present in the air that we breathe. It's about 3% of air is carbon dioxide, and it's actually going up. This is one of those reasons for climate change. Not the only one, but one of them. About 100 years ago, if you were to measure the amount of carbon dioxide in this room, you would have discovered that there were about 300 parts per million CO2. Today, you'll be lucky if it's below 400. Pure air is now 100 parts per million more concentrated in carbon dioxide than 100 years ago. So when you have people that deny climate change, there's no better evidence than to show that that's going up. And it's going up because we're making it. Carbon dioxide is a greenhouse gas. We make it by burning fossil fuel, by doing many other things that generate this gas. Not to mention growing cows. You know, for beef, for ground beef, if you eat meat, you know what I'm talking about. Cows produce a lot of carbon dioxide, along with another gas called methane. Anyway, I don't want to get on my soapbox. You get the idea that these guys are called compounds. They're made up of elements, but they're pure substances. They're pure substances. Now, any questions about that? A compound is always going to have a formula. Oh, let me give you one more that I did talk about on Monday. This one I'm going to put on top. It has a bigger formula. But it's something that we all need every day of our lives. So this compound has carbon, has hydrogen, and has oxygen. A little bit more complicated than the other examples. not only has carbon, hydrogen, and oxygen, it has 6 carbons, 12 hydrogens, and 6 oxygens. Anybody knows what that is?
Air.
Air. Let's put air over here because air is going to be a mixture. We're going to talk about air. It's not air. Let me just put here air. It's a mixture as a reminder. I don't think we need the periodic table right now, so let me erase this. Any other guesses? That's not a bad guess because what I said we all need it every day. I mean, that's very good thinking. There's no reason why you should know what that is, by the way. I mean, if you have never had chemistry, there's no reason to know it. But I'll entertain another. I'll give you a hint. It's a sugar. And it's a sugar that some people have to be watching every day. Glucose. So this is glucose. The brain, the human brain, needs glucose, and it cannot make it. It has to get it from the bloodstream. Without the other parts of the body supplying glucose to the brain, we couldn't function. So glucose, as bad as sometimes it has a bad reputation because people that suffer from either diabetes, I'm thinking in Spanish, suffering from prediabetes or diabetes have problems with glucose, you still need glucose. No matter what, no matter how sick you are, you still need glucose. So your problem is not glucose, your problem is a hormone that you don't produce or that you cannot recognize, and that hormone is insulin. But that's another story. At this point, what I want you to realize is that molecules can get very complicated. Compounds can get very complicated. That's a simple one. There are compounds with thousands and thousands and thousands of ingredients, but they are all composed of elements, and they all have a formula. If they don't have a formula and they're not composed of elements, but they're combined with other compounds, then we're going to talk about mixtures. Two kinds of mixtures. We're going to talk about something called a homogeneous mixture and something called a heterogeneous mixture. And air is an example of a mixture. Now, let's first define the two terms, homogeneous versus heterogeneous. Homogeneous basically means one very simple thing. The mixture that you have in front of you cannot be distinguished by its ingredients. Let me see if I can word that a little bit better. Maybe with an example. If I take a glass of water, so there's water here. I have a pure substance. I have a compound, right? We said that earlier. But what happens if I add another chemical here? Something that you may recognize. This is another compound, by the way. And some of you may know what that is. Sodium chloride, table salt. The salt that you add to food to make it taste better, that's what it is. So if I add that to water and I stir that, and then I put the glass here, and then next to it I put another glass with just plain old water, can you tell them apart? Can you just by looking say, oh, that one has salt? Not if you mix it really well. I mean, you have a very good point, because if you take salt from the ocean and you mix it with the water, it's going to be cloudy. And I'm glad you mentioned that, because this distinction sometimes is not that clear-cut. Homogeneous means that there's no cloudiness. It's completely even. The mixture looks like it has only one ingredient, but it doesn't. Does that make sense? So a homogeneous mixture is one that you cannot tell the ingredients apart. The only way to tell apart the water and the water salt is to taste it, or to evaporate the water, and that will leave the salt behind in the one that has salt. The other one will look empty. So a homogeneous mixture, a mixture in which you cannot tell the ingredients apart. Air is a homogeneous mixture, because even though we cannot see air, if we could, we would not see the differences in the mixture. The mixture of air contains nitrogen, which is an element but is also a compound. It contains oxygen, and it contains CO2, plus many others in minor amounts. Air as a mixture is homogeneous again because we cannot tell the ingredients apart. It's about 79% nitrogen, about 20% oxygen, about 0.3% carbon dioxide, and then tiny amounts of many other things. But it's mostly nitrogen, and that's what we breathe. Nitrogen doesn't do anything to you. It comes in and it goes out just unchanged. But it is a mixture. So what is a heterogeneous mixture? A mixture in which you can tell the ingredients, or you can at least see that there's more than one thing, 2, 3, 4 things. Now, sometimes in the homework problems, there are tricky questions. I don't like them. I try to avoid them. But sometimes they do show up. As you can imagine, the questions in the homework and the questions in the quiz, I probably created 10% of them. The other 90% was created by somebody else and put together as a package for us to use. Later in the course, you're going to know which ones I modified, because the name of the question has the word copy. And that means that I changed it a little bit just to make you think. I'll tell you more about that in a future meeting. But one of those tricky questions is like this. Classify the following into homogeneous or heterogeneous. And then the first example that you're given is spaghetti sauce. Spaghetti sauce. Well, what would you answer? Is spaghetti sauce a homogeneous mixture, or is it a heterogeneous mixture? It depends on who made the spaghetti sauce, really. I mean, if I get very picky about it, I may say, okay, you know what, I don't like to see chunks of tomato or of onion. I'm going to take my spaghetti sauce and blend the heck out of it. I'm going to put it in a blender for 5 minutes until it's smooth. And then I take a look at it. I cannot tell the ingredients apart, right? So it's a trick question. I agree, it's mostly a heterogeneous mixture in most spaghetti sauces. But what about ketchup? Is that homogeneous or heterogeneous?
It has to be heterogeneous because it has multiple ingredients.
It does have multiple ingredients, but can you tell them apart when you look at it? Then it's homogeneous. That's how you define it. Not because what you know is in there, but because what you can see. That's a key. You just made, thank you for that. In your brain, you know that ketchup has many ingredients, so you're going to say heterogeneous. If you cannot see the different ingredients, you're going to call it homogeneous. What about mayonnaise?
Same thing.
Exactly. If it's very well mixed and very, very well made, it looks like one single thing. So it's homogeneous. But if you start adding garlic because you want to make aioli, then it's going to be heterogeneous.
Because you can see the garlic.
Because you can see the garlic. So if you see the different ingredients, I mean, that coffee that you're drinking, open it and look at it.
Interesting.
What, is it homogeneous or heterogeneous?
It has to be homogeneous.
Exactly, because you cannot see. But for instance, that other coffee from Dunkin' Donuts, I can see the ice floating. Yeah. And the sugar in the bottom. So if I see the ice, That's heterogeneous, right? Let's just leave it at that. So if you can tell that there's more than one ingredient and it's a mixture, then it's a heterogeneous mixture. If you cannot, then we're going to call it homogeneous. And if you have a question in the homework or the quiz that you are sure that you answered correctly, you just tell me and I'll fix it. I don't want you to get points off because of that subtle difference. Okay. Now that we have talked about matter and the classification of matter, let's talk about the properties of matter. And actually, first, let's talk about the states of matter. So we're going to stay with water as the example because it's a very convenient example. Water is a pure substance, a compound, but water can exist in 3 different physical states. It can be ice, which we're going to call a solid. It can be plain old water, which I'm going to have to call a liquid, because I have no better way of describing it. And if evaporates is a physical change, not a physical state. We're going to distinguish that very soon. If it's a mist or a steam, we're going to call it a gas. So there are 3 states of matter: solid, liquid, and gas. Now, the 3 are important because when you study chemistry, sometimes you mix things that are solids. You sometimes mix things that are liquids. Sometimes you mix solids with liquids. Sometimes you even mix liquids with gases. So you need to understand what state of matter a sample is in so that you can set up the proper conditions for that mixing to take place in an efficient way. Now, let's take a look at the 3 as far as 2 properties. One is going to be the volume, and another one is going to be the shape. And please, let's not split hairs. We're going to try to be very generic about it. Now, let's imagine that we have an ice cube, and it's really, really cold. So we are way below the freezing temperature of water. So it's not changing, it's not melting. Let's put it to you that way. Is the shape of that ice cube changeable if you keep it frozen? Is it changing as you look at it? If it's solid frozen and you don't do anything else?
No.
So the shape of a solid is definite. Is definite, or fixed, if you will. It has a fixed shape. The volume of a solid is also definite or fixed. In other words, that ice cube, as long as it doesn't melt, it has a certain volume and it doesn't change. So the volume is also definite or fixed. That's a solid. If you want to see how it's different from a liquid, well, let's take a look now at that ice cube that has melted. And let's imagine that we put it right here on this table. We wait 5 minutes, and that has now melted. What happened to the shape? The shape changed. It's actually now the shape of the table is spread. So liquids don't have a definite or fixed shape. They have a variable shape. However, the volume does not change. Even though that water has spilled over, the amount of water, the volume of water is still the same. If I collect it all back and put it back in a container, it's going to measure the same volume as before. So the volume of a liquid is also definite or fixed. Finally, a gas. So let's think of a balloon filled with air, not with helium, but with air. So it has a certain volume, right? What happens if I open the balloon or I pop it? What happens to that air? That air goes everywhere. So the volume and the shape of a gas changes. It changes with the shape and volume of the container. So this is variable, and this is variable. And the reason for that, there's actually a really good picture in one of the lecture notes. Let me see if I can find it very quickly for you. It's a cartoon that shows you this in a visual way. Is there here somewhere? I guess it is here. Except that the solids doesn't have it. Oh no, it does. Just to make sure that we visualize it. Oh, I don't need that. We're going to take a look at a solid and why the volume is definite and the shape is definite, and then a liquid, and then a gas. And these are cartoons. These are just drawings. Okay, so here is a solid. Those little circles, those balls, these little circles are the ingredients, the elements of this particular sample. Notice that they are very close to each other. They're compact. They're touching each other. That happens only in a solid, and that's why the shape and the volume doesn't change. So that rock has that shape and it has that volume, it doesn't change. In a liquid, the ingredients are a little bit separated. So you may not be able to see it, but here they have water with a red circle and then two white circles. And that's one water, that's another water, that's another water. They're not touching each other. They're close, but they're not touching each other. Now, if I cool this down, they're going to start touching each other. That's a solid, that's ice. But in the liquid state, there's a little bit of space between the ingredients. And that's what makes the shape variable. Finally, in a gas, the ingredients of a gas not only are all separate, there's more space between them, but they're moving super fast. The molecules, the ingredients of solids and liquids are not moving hardly at all. They're moving very little, and that's why their shape doesn't change. But in a gas, they're moving like crazy, and there's a lot of space between them. The more you leave them out, the more space they can occupy. Okay? Now, that's essentially what I want you to know about this, except that you mentioned the word evaporation, right? Somebody did. Diana, you did, right? So let's talk about what evaporation is and how it relates to these three states of matter. So, we're going to, well, let me just use this drawing. We're going to now talk about these guys. And this is going to bring us into the discussion of temperature, which is kind of nice. So we have a solid, we have a liquid, and we have a gas. If we stay with water as example, a solid can become a liquid, and a liquid can become a gas. We'll talk about water doing that in a minute. But the same can happen in reverse. A gas can become a liquid, or a liquid can become a solid. Now, what is necessary for these changes to take place? A change in temperature. Temperature is a measurement of the amount of heat in a certain sample. So if I start very cold, that's a low temperature. But I go to hot, a high temperature, I'm going to start going from ice to liquid water to steam, depending on the temperature. Does that make sense? Now, the transition point, when a solid becomes a liquid, has a name. We're going to call it melting. Just like you call it for water, for ice melting, you can have oil melting. Or you can have this marker melting if I heat it up. That means going from a solid to a liquid. Every substance has a melting point, which is a temperature. In the case of water, that happens to be 0 Celsius. We'll talk about that in a minute. 0 degrees Celsius, water changes from solid to liquid. Now, when the liquid becomes a gas, that was the word that we're going to use, evaporation. And we're just going to use that one. I mean, we could use boiling, which is actually acceptable. But both mean the same, changing from liquid to a gas. When something evaporates, it means that it goes from liquid to a gas. When something boils, it means that it goes from liquid to a gas. Now let's talk about the reverse process. When you start cooling things down, now you are removing heat, cooling things down. What is this process? We see it often in the morning when we walk out the door. Certainly this morning I saw a lot of dew. Condensation. You see it on your cold drinks. That water outside was gas in the atmosphere. If you take that drink to the desert where it's really dry, there's not going to be any condensation because there's no water in the air. But if you go next to the ocean where there's high humidity, start sweating more because there's a lot of there's a lot of water in the air that is a gas, and now it's condensing. So many of these things you knew, you just didn't know that they were part of chemistry. Or maybe you did, but we are reaffirming that. Now, when a liquid becomes a solid, the most common word is freezing, and that's acceptable. There's a little bit more of a technical word, solidification, to become a solid. So when water in the liquid form becomes a solid, ice, it freezes. But I can also freeze oil. Okay? Now, this was removing heat, this was adding heat. Under certain conditions, and it actually happens to a substance that you're going to start seeing the closer we get to October 31st, you can go straight from a solid to a gas without going through liquid. That has a name. Or you can go from a gas straight to a solid without having to go through the liquid state. It only happens under certain conditions and to certain substances. You guys know what dry ice is? So, what happens when you see dry ice in front of you? What does it do? It's like smokes. It's not evaporating though. It looks like it's evaporating because that would be a liquid. It also looks like it's boiling, but it's not boiling. It's actually going.
Watch it burns you, correct?
If you put it in water, you're going to see bubbles, yes. But it's a solid. There's no liquid. So it's going straight from solid to gas. That is called sublimation. It has a name. I'm sorry. Sorry, it's a new word. I mean, you can probably use it in plain old English and say, hey, wait a minute, don't sublimate. Means don't get excited. Don't get too angry. So sublimation means to go from a solid, as in dry ice, to that steam, or what do you call it, smoke? It's not really smoke, but it looks like smoke. Did you know that dry ice is carbon dioxide? It's a solid form.
Isn't that why, like, if you're putting it in water, sometimes, like, you can, like, touch it and, like, it doesn't, like, burn, but, like, you get, like,
yeah,
feeling to it.
absolutely. And there's, oh boy, I wish we had, access to liquid nitrogen. Liquid nitrogen is even more wicked than dry ice. Liquid nitrogen, is a liquid, but it's nitrogen, the gas. If you take like a flower, like maybe a rose, and you dip it into liquid nitrogen and pull it out, it still looks like a rose, but if you flick it, it shatters into pieces because it freezes so fast that it destroys the cellular. We used to make actually ice cream using liquid nitrogen. You make ice cream in like 1 minute.
Can that be, like, the only lab?
Yeah, I know. If I can get some liquid nitrogen before the end of the semester, I will certainly at least do a little bit of a demo. The professor that used to use liquid nitrogen in some of her classes left. Her name is Katie Ruggieri. And, but I'm going to see if I can get it.
I'm waiting for it.
Okay, my goodness.
Will,
Maybe we'll get even some dry ice.
will liquid nitrogen will do that to flesh?
Oh my God. If you stick your finger in liquid nitrogen, it will kill it. It will really, really, really hurt it. I mean, I don't even want to think about that experiment. Yeah. If I spill, well, let's wait until, now you're going to make me get some liquid nitrogen.
Have you seen it? It's like
Oh, yeah. Oh, but I don't remember that scene.
exactly the same.
Oh,
It's
God.
actually some type of compounds and
Good old Arnold, huh? I don't remember that scene. I'm going to have to look it up.
yes, exactly just like that.
I had a student that took this course that at the end of the semester she came to me and gave me a movie. And it wasn't the Terminator. It was, God, I'm trying to remember it's Robin Williams. Lots of chemistry in that movie. Flubber? Flounder? Flubber? Something like that. I don't remember, but I thought it was a really nice gesture. Yeah, with Robin Williams. Okay, so now you have, oh, never mind, I have one left. So going from a gas straight to a solid, which is the reverse of what we were talking about, is actually called deposition. It's not like a lawyer having to interview you and you had to tell the truth. No, this is different. This is to deposit. A gas becomes a solid through the process of deposition. Okay, now that should bring us to the idea of physical changes, and then we're going to have to compare and contrast that to chemical changes. So a physical change is almost anything that you see here, is changing a substance from one state of matter to another. A chemical change transforms the substance into something else. Let me give you a preview of things to come. We talked about hydrogen peroxide, H2O2. When you have it in your kitchen cabinet or in your bathroom or wherever you have hydrogen peroxide, If you leave it there for a long, long time, it actually changes itself little by little, very slowly, into water and oxygen. Now, if you don't believe me, look at the expiration date. That expiration date tells you that this thing is not going to be hydrogen peroxide after a few years. If you want to prove to yourselves that that is in fact happening, take a little bit of hydrogen peroxide and put it down the sink, and it's going to start bubbling, fizzing. Don't do it on an open cut because it hurts, but it does that. Whenever there's dirt, it bubbles. It doesn't hurt?
No, it doesn't hurt. Actually,
Oh.
it doesn't. I heard you can clean a cut with hydrogen peroxide, correct? Instead of
You can. It's a very nasty chemical, so it does kill microbes. Yes.
Stings. I hate that one.
Yeah, alcohol is worse. You're right, but hydrogen peroxide, in my experience, it does hurt a little bit. Maybe not much. Okay, but anyway, my point is that this guy becomes those two guys, and this guy is no longer this guy, is now that. This is a chemical change. You have now one compound turning into two different compounds. This is not like melting water or freezing water. This is a complete different story. There's a transformation, and this is a chemical change. So when you do the homework or the quiz, you're going to have questions like, okay, is the change of a nail from being shiny to being rusty chemical or physical? Well, you need to think about what's going on. It's both, yes. It's a bad question, just like the homogeneous and heterogeneous question was, because it's also open to discussion. For the most part, the books want you to answer chemical change, because the shiny nail was iron, Fe. When you add oxygen, the shiny nail now gets oxidized into something called FeO, iron oxide. That's rust. This is not rust. That's why it's a chemical change. You wouldn't know that just by looking at the shiny to rusty. So you need to be told to look for certain things. Well, there is a list in the presentation that gives you what to look for to determine whether or not there's a chemical change taking place. Actually, it's not. I don't see it on the presentation. So let me Google it. And very briefly, in 3 minutes, we'll talk about it, because it's going to help you with some of the questions. Come on, stay. I guess I'm not going to use it. Evidence. Some of them are really obvious, some of them are not. Let me see. I think this one has enough.
Perfectly organized. I'll start working on my thesis.
Hey, lower
What do you do to
volume.
ensure you feel confident nailing your final
Forget
thesis?
it. Is that a commercial? Oh yeah, skip ads.
All right, it's reaction time. We're going to be looking for evidence of chemical reactions. So, here's proof. How about a color change? Is another clear gas, for instance?
Hold on, I'm just trying to go to the
So, what is
end.
it? 2, one of the most important mass from, in other words, math, separate water molecules.
Sorry, you
which
guys.
leaves you with a bunch of.
I thought it was better than that. Okay, evidence of a chemical reaction. They're right here. You don't need to memorize these. This is just a useful tool to have. So when you mix two things, sometimes you need to determine whether that mixture is undergoing a physical change or a chemical change. Is there something going on beyond just mixing two things? Like when I gave you the example of water plus salt. When you mix water and salt, there's no chemical change because you can recover the salt away from the water by simply evaporating the water. So that mixture was a physical change, not a chemical change. So when is it a chemical change? When you see one of these things. You mix two things and bubbles form. A gas comes out. Maybe you've done this at home, baking soda and vinegar. If you mix baking soda with vinegar, it starts fizzing. That's chemical. There's a transformation. If you observe a color change, you mix two things. One was colorless, the other one was a... You mix them and now it's purple. Chemical change. If you mix them and the yellow mixes with the colorless and it just becomes a paler yellow, it's a physical change. There was no change in color. It's still yellow. Now it's just lighter. This one is kind of weird, this word precipitate. Precipitate basically means to form a solid from a liquid. When you mix two substances that are liquid and all of a sudden clumps come out, it clumps, that's a precipitate. So that's a sign of a chemical reaction. It's as straightforward as that. If you mix two things and they get hot, what is it called, icy hot? What is it that you can buy at a pharmacy for when okay. So that is a chemical reaction. When you break the package to get it hot or cold, there's a release of energy or an absorption of energy. That's a chemical change. You cannot get them back. When you cook an egg, chemical change. The egg is now cooked. You cannot go back. There was a chemical change. So in other words, if you can reverse the change, it's physical. If you cannot reverse it, it's chemical. Let's not complicate it more than that. That's it. All right, so now we're ready for the discussion of temperature. And this is going to take no more than 10 minutes, which will then take us to the last part of the chapter, energy. I know it's a lot of material for one day, but when you review it, I think you'll find it intuitive. You'll find that it makes sense. It's not that complicated. And there's no need to memorize things, okay? In fact, let's talk about temperature. So temperature is an indirect way of measuring heat. Okay? Now, before we talk specifically about temperature, let's talk about the three scales of temperature that you are familiar, that you may be familiar with, or that you're going to have to be familiar with at the end of this discussion. So Fahrenheit is one scale. Celsius, also known as centigrade, is another scale. And finally, one that you may not be familiar with, Kelvin. By the way, these three are last names of the people who invented the scales. Now, let's stay with water. And let's talk about the boiling point of water in these scales. And then we're going to stay with water and talk about the freezing point of water in those three scales. You're probably pretty familiar with the temperature at which water freezes in Fahrenheit. right? I mean, winter is coming, some water is going to freeze outdoors. What temperature is that? When do we know that water freezes in Fahrenheit?
32.
You never gave it a second thought, huh? It's freezing outside. That means not only is cold, but that water is becoming a solid. So I heard the number, 32 degrees Fahrenheit. Okay? Bless you. At what temperature do you think water freezes in Celsius? Anybody knows? I know because I have lived in two countries, one that uses the Fahrenheit scale and one that uses the centigrade scale. I used to go outside in my hometown in the middle of winter. It rarely became below freezing, but sometimes it did. In the middle of January, we could have temperatures of 20. So to me, it was fascinating to leave a glass of water outside and then go out in the morning and see it as a solid. To you guys, it's like, wow. I mean, you grew up here, many of you, not everyone. That temperature is 0 Celsius. The freezing point of water is 0 in Celsius, 32 in Fahrenheit. There's no reason for the two other than their different ways of measuring temperature. In Kelvin, it's 273. Now, check this out. I put a little circle and an F for Fahrenheit, a little circle and a C for Celsius. That means degrees. Degrees Fahrenheit, degrees Celsius. Kelvin doesn't use the degree. It's just the K. There's a reason for that, and I'm going to explain it to you in a minute. So no degree symbol for Kelvin, but that's the temperature at which water freezes. Now let's talk about the point at which water boils. Anybody knows in Fahrenheit? 102 in Fahrenheit? Well, 102 Fahrenheit is really hot, right? But it's not going to boil water. A little bit higher. 212. 212 is the temperature at which water boils in Fahrenheit. In Celsius, 100. You see the metric connection? Multiples of 10. 100, 0. I mean, that's where it ends, but you can see that Celsius picked water when he defined his scale and decided, okay, the boiling point of water is going to be 100, the freezing point of water is going to be 0, and that's my scale. Fahrenheit did a similar thing. But what he did is the following. He said, okay, the temperature of my wife is going to be 100 degrees. The temperature of my wife right now is what I'm going to call 100 degrees. So guess what? His wife had a fever when he invented his scale, because the body temperature without a fever is 97.98, 97.6, right? I mean, it varies a little bit from person to person, but it's around 98, 97 and a half. 100 is a fever. A light fever, a small fever, but it's a fever. Anyway, there's no reason why Fahrenheit did what he did, so we're not going to go beyond that. Now, what about Kelvin for the boiling point of water? 373. So 100 more. There's a linear relationship between Kelvin and Celsius, not between Kelvin and Fahrenheit. So these two are metric, if you will. Now, we can, yes, go ahead.
Why don't we see Kelvin that often? And we all usually see Fahrenheit and Celsius more often.
Well, one of the reasons, of course, is because there's resistance from the public to use a different scale than what you are used to. So for instance, you see Celsius sometimes in the US, but it's probably under the context of a classroom. You don't hear the news telling you, oh, the temperature outside today is going to be 25 Celsius. And that's because people don't want to switch to Celsius. Same thing happens in other countries. You use Celsius because that's what is used there for hundreds of years. Kelvin is a very convenient scale, but nobody wants to use it. I don't know if in England uses it, or Australia, or China, or Japan, but it's a very useful scale for chemistry. Why is that? Let's talk about that for just 1 minute. Things can get hot endlessly. You can keep adding heat, energy, and heat things up. As hot as the sun, or even hotter. However, cooling things down is a different story. There's an absolutely minimum temperature in the universe that you cannot go below. In other words, in a certain scale, and it happens to be the Kelvin scale, there's no negative temperatures. So 0 Kelvin, and I put a 0 because if I just put 0 and then the K, it looks like I'm saying okay. No, 0 Kelvin is absolute 0. Absolute 0. Nothing in the universe can get colder than that. How come? Well, because at the end of the day, temperature is a measurement of how fast molecules are moving. The faster they move, the higher the temperature, the higher the temperature. The less they move, the colder the temperature. Well, what happens when they don't move anymore? When they're completely static, there's no more heat to extract. There's no vibration anymore generating heat. That's 0 Kelvin. That's absolute 0. And it happens to be in Celsius minus 273. Do you see that? So you subtract 273 from this, you get to negative 273, which is 0 Kelvin. I don't care about Fahrenheit. I don't know what it is. Now, you shouldn't care either. And here goes something that some colleagues of mine disagree with. I think it is the way to go. When you get to the part of the homework where you need to make conversions, we've been doing conversions almost from the beginning of the semester, right? Conversion factors, conversion factors, conversion factors. Well, the formula to convert Fahrenheit to Celsius is really tricky. It's, I would say, almost complicated. Please don't use it. Use your smart devices, use the internet. If I give you a problem and I ask you, or the homework gives you a problem, what is the temperature of the outdoors, which is right now 80 Fahrenheit in Celsius? Don't use the formula, please. You do yourselves a favor and just ask the internet. Now, check this out. In fact, let's prove that. Why don't you ask your smart device, if you have one right now with you, what is the temperature in Celsius of 80 Fahrenheit? So what is 80 Fahrenheit in Celsius? That's how hot it's going to be today. About 80 Fahrenheit. So what's that in Celsius?
26.6.
26.6, okay, so 27 almost, right? Celsius. To get to that answer with the formula, you would have to multiply by 1.8 or by 9/5 and then add 32. No, sorry, the other way around. Divide by 1.8 and subtract 32. That's too complicated. Now, I used to give this problem in quizzes. And of course, I was hated for it. Can you please tell me, using your smart device, what is negative 40 Fahrenheit in Celsius? what's negative 40 Fahrenheit in Celsius? And they used to have to use that formula, by the way. They had to do it with math. Come on, be brave and tell me the answer. What is negative 40 Fahrenheit in Celsius?
What is the formula? Can you put that?
So I'm going to put it on the board. Sure.
Is it like 40 Fahrenheit, negative 32, correct?
Yeah.
When you want to find the Celsius, correct?
I'll show you the formula. But using your smart device, what is negative 40 Fahrenheit in Celsius? Thank you for being brave enough to say what is the correct answer. It's the only temperature at which the two meet. So this is the only temperature in which the two are the same. There's no other temperature. Negative 41 Fahrenheit is not negative 41 Celsius. Trust me. So when I used to have this question in the homework or in the quiz, and students were actually under the pressure of the clock because it was a 20-minute quiz or what have you, and they would see the answer, negative 40. Why am I getting the same number? They really hated me. I mean, I think I hated myself. It's not fun to have an answer that makes you hesitate. But that's the only temperature in which that happens. Now the formula, since some of you are curious about it, is in the lecture notes. And you can use it. I mean, it's a good mental exercise. Almost there. There it is. That's probably way too small. But to get Fahrenheit from Celsius, you multiply the Celsius temperature by 1.8, and then you add 32.
If I want to get,
This is to go from Fahrenheit to Celsius.
if I want to go from Celsius to Fahrenheit,
If you want to go from Celsius to Fahrenheit, then you need to divide, but after subtracting 32. So first you subtract 32. So let's do it for this. So we have negative 40 Fahrenheit. We're going to subtract 32 from that. So minus 32. Okay, what does that give you? Negative 72. And then take that number and divide it by 1.8. It's going to be 40. You're frowning.
Oh, I just, the top one says to get Celsius to Fahrenheit, it's worded here.
Oh yeah, this is a mistake.
The top one, which one is?
This is right. Converting Fahrenheit to Celsius, you do this. To convert Celsius to Fahrenheit, this is a mistake. You just discover a mistake. You use this formula. I'm not explaining it right.
Well, it looks like it's saying the opposite. It says to get Fahrenheit from Celsius would be getting. Never mind.
Yeah, no, but you're right. So ignore the headings, just look at the formula. So if you have Celsius, this is the formula you use to get Fahrenheit.
Right.
If you have Fahrenheit, this is the formula you use to get Celsius. I'm sorry, the headings are probably wrong. Huh?
are you sure?
Yes.
I think it's correct.
Well, it may be correct, but the formulas are correct.
Yeah. The wording of the heading.
So the wording is a little strange, yes. Yes, because it's actually saying exactly the same. You see? To obtain.
No, it's correct.
Yeah, it is correct.
It's just worded.
It's worded weird. It is correct. But anyway, don't look at the heading, look at the formula. If you want to practice it, by all means, but I'm not going to be thinking less of you if you use the internet. Certainly not for converting temperatures. Okay, so that basically brings us to the last part of the chapter, which is talking about energy. So now, while I erase this, can you please try to come up with a definition of energy? So this is the last topic of chapter 3. It's a little bit of a... What was that? Okay, so that's an example, not a definition. But I agree. Electricity is a type of energy. What do you use electricity for? To power things. Correct. So energy can be, in very simple terms, be defined as the ability to do work. That's it. What type of work? You name it. Ability to do work, on quotes. The ability to power something, to push something, to move something, to raise something, to destroy something, even to build something. And we're going to simplify the kinds of energy to two major types of energy. We're going to talk about kinetic energy and potential energy. And I'll give you an example of both. You can probably think of more than two. Potential energy is energy stored in something.
Batteries.
Say that again?
Battery.
A battery has potential energy. Absolutely. A battery has potential energy. This marker, when it's sitting on this table, has potential energy given to gravity, because if it moves away from the table, it's going to fall. That potential energy became kinetic, which is movement. So kinetic means movement. Potential means stored. In very general terms, okay? This is not going very specific. So which of these two would you say solar energy is? Well, it can be both, right? Solar energy can be stored into batteries, or it can be used to light up a lamp. So it can be used as both. Chemical energy. Batteries contain chemical energy. So lithium batteries contain lithium, which becomes something else when releasing energy. Now, there is a very special type of unit to measure energy. We're going to talk about two, but I want you to think of one primarily, because it is a useful unit of energy. So, energy units. How do we measure energy? Remember that we measure distance with the meter, or with the inch, or the foot. We measure volume with the gallon, or the ounce, or the liter. How do we measure energy? Volts. That's actually a compound energy type of unit. So it is related to energy, but it's not the basic unit of energy.
Time.
And time goes with volts to a combination. We actually use calories. Does that make sense?
No.
I mean, you need calories to do work. And one that you may not be familiar with is called joules. Now, calories become a little tricky, simply because, the U.S. sometimes does things a little bit different from the rest of the world. So when you travel abroad and you look at a label on a food item, Labels are supposed to tell you how much energy there is in the food. And let's talk about it for a second here. What are the 3 macronutrients that are listed in every label? Carbs, fats. So sugars are carbs and proteins. Those are the 3 macronutrients then you have vitamins and minerals. Those are micronutrients. Those are not, they don't provide energy. These guys provide energy. Now, how much energy? Carbohydrates, for every 1 gram of carbohydrate, you get 4 calories, which are really kilocalories, but let's just call them what the US calls them. 4 calories per gram. I heard the 9. So yes, for fat is 9, so twice as much energy in a gram of fat. And proteins, what did you say? Is also 4. It is not a trick question. It's also 4. The same amount as carbs. Now, that doesn't mean anything about sugar levels in the blood, nothing like that. It's just the amount of energy that is provided by those 3 macronutrients. Now, remember that these are actually conversion factors. We're saying that you can have 4 calories per gram or 1 gram per 4 calories, because those are conversion factors. Same thing for that, same thing for that. So if you look at a food label, you can actually verify whether or not the stuff that they're showing you is accurate. Let's take a look at one food label here and then do a quick calculation. Is that going to be visible enough? So we're going to do a quick calculation to verify a label. I'm going to leave that there because we're going to need the joules soon. This label, I don't know where it comes from, but it says it has the number of servings, the serving size. It's actually quite well explained. Come on, please stay. If not, I just hold it. So it's explained in different ways. Serving size, 55 grams. Number of servings per container. That's sometimes really interesting because the way companies that make products that are really bad for you get away with it is by hiding that in small numbers, and basically, you get, I don't know, ding-dongs or whatever, I don't know, some of these really bad sweets, and it's like 50 servings, when in reality, is one cookie is like 5 servings. So you need to cut the cookie in 5 pieces to have 1 serving. It's terrible. Anyway, let's see if these numbers are right. So this guy has 8 grams of fat. So what is 8 times 9? That's going to give us the calories. 72. Fat, 72 calories. It has how many carbs? Total carbs, 37. So what is 37 times 4? 37 times 4, 120, 148? 148? Okay. 148 calories are coming from the carbs. Is there any protein on this one? Yeah, 3 grams. So 3 times 4, that's an easy one. 12. Let's add them together. So 10, 12, 8, 12, 13, 232 calories. So not quite the 230 that we see here, a little bit more, but it gives you an idea. I have never discovered a mistake in a label that is like huge, but I have on occasion. There is a beef jerky that I used to buy that said that it had a certain amount of salt, of sodium, but it was actually like 10 times that amount. So it was completely mislabeled. I had to actually write a message to the, because you were misleading people by 100%. It was 10 times that amount. But for the most part, this gives you a very good idea. If we add the fat and the carbs and the grams, it doesn't give you 55 because there's also water in there. These are things that are not completely dry. So what is 8 plus 37 is 45 plus 3 is 48. So there's 7 grams of water per serving of whatever this happens to be. I don't even know what it is. It doesn't say. Anyway, okay, now, if you were to look at a label from a foreign country, let's see Portugal. I have never looked at a food label from Portugal, but let's see if we can find one. What?
The food is so much like healthier, like for your body.
I think you're probably right.
My,
It's less processed for sure.
my mom just spent 2 weeks there, and she was just like telling us like when she got back, like how different it was, and how like her like body just felt different, like eating that food compared to how processed it.
It's just that, look, and don't get me on my soapbox because when I was a graduate student, we used to get grant money from a company called Monsanto. If you never heard of Monsanto, it's evil, it's bad.
Yeah, that's a bad.
It's a bad company. And we used to get millions of dollars in grant money. They make pesticides, like Roundup, I think. Another company that, in fact, when I was a graduate student, I could not criticize Monsanto or they would sue me. You could not say a single bad word about that company or you would be sued. The same thing is true for ADM, Archer Daniels Midland. They have the whole market for sugars, high corn fructose syrup and all of those nasty stuff. I can't believe that I'm recording that, but anyway. There's a movie with Matt Damon called, oh my God, what is it called? He's a whistleblower for the food industry. And he goes to the government and says, these people are cheating. It's terrible what they do. The Informer, I think it's called. It's an old movie. It was from the beginning of his career. But anyway, the point is that, yes, in countries like Portugal and many other countries, there's a little bit more of an effort to try to live healthy. I couldn't find a Portuguese label right away. Let me show you one from Mexico just because they have something that is somewhat recent and they get a lot of pushback from the food industry right here. Every type of food, in addition to the label where you can find the nutritional information, has these black, nasty signs saying there's an excess of calories in this food, there's an excess of sugars in this food, there's an excess of saturated fat in this food. And it's just like, it's almost like the warning in cigarettes that tell you cigarette smoking will kill you. It doesn't say it may. It tells you it will kill you. These labels tell you up front, if you eat this, you're putting your health in danger. I mean, because of those things. And it's from the health secretary, or Department of Health, whatever. And of course, the current government there is a little bit on the left. So they're getting a lot of push from the right, which is more capitalistic. Yes, go ahead.
I found this app, right? You scan the barcode of like whatever you're buying at the store.
Okay.
Or products, whatever. Like it tells you how poorly that product is. Like if
Well,
it's good for you. If it's
share it with us. What is the name of the app?
Yuka. I use it for everything.
What is it called?
Yuka.
Spell it, please.
Yuka. So it tells you if it's like organic stuff, natural stuff. Like
Oh my
it
God.
tells you everything that's like inside that product or the food, whatever it is. You know how you go to the store?
Yeah. And you scan them?
Yeah.
Well, I'm going to be using Yuka this afternoon for sure.
Yeah.
Thank you for sharing that. Is it Ashley? No.
Jane.
Jane. Okay. Thank you. All right. So anyway, we did a problem. The last thing I want to say about food labels in other parts of the world are that they use joules instead of calories. And there's a reason for that. In the United States, they use this word. In other countries, that's equal to 1,000 calories. The difference is capital C, lowercase c. So what is 1 calorie in the US equal to in other countries? Is equal to 1 kcal. 1 kilocalorie is really a calorie. Now the calorie has a really interesting definition. And I'm going to leave it at that because that brings us to the last part of the chapter, which I did not have a chance to cover in the Monday class, so I'm going to leave it for later. It's called specific heat. But let me just leave you with this thought. The definition of calorie is quite straightforward, and is based on water. Is the amount of energy, so picture this, that is needed to increase the temperature of 1 gram of water 1 degree Celsius. So think about it. You have a container, you put 1 gram of water, which is it's like a drop, and then you start heating it up. The amount of heat that you add to bring the temperature, let's say from 20 Celsius to 21 Celsius, is equal to 1 calorie. I'll repeat it one more time. Is the amount of energy required to increase the temperature of 1 gram of water 1 degree Celsius. It's as simple as that. Sounds complicated, doesn't it?
I'm sorry, I'm lost. Can you repeat that?
Right. Here it goes again. 1 calorie is equal to the temperature, the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So if you have 1 gram of water and you increase the temperature of that 1 gram of water by 10 degrees Celsius, you use 10 calories. 100 calories, 100 degrees. You can also change this to grams. 100 grams, 1 degree, 100 calories. So maybe what you want to do is copy this and then try to process it It's not that it's important, but it's a very simple definition based on water once again. We use everything based on water. It's such a useful substance. Okay, so the last part of the chapter, I'm going to leave it for when we come back after break. And after the holiday break. And it's going to be specific heat. So if you run into problems when answering questions in the homework, I'm going to move the deadline to October. When do we meet next? By the way, if you were late, there's no class next week. So we're meeting 2 weeks from today.
18th.
October 18th? Okay, so I'm going to move.
The Wednesday is October 18th.
Okay, so the Wednesdays, I'm going to move the deadline to the homework and the quizzes to October the 22nd, that Sunday, after we come back. And don't worry, we're not going to fall behind. We can catch up later.
Is that for chapter 3?
That's for chapter 3, yes. Chapter 3.
Chapter 3 until October 18th?
Yes.
Okay.
We're going to finish chapter 3 on October 18th and start chapter 4 on October 18th. Because the last part of chapter 3 is very short. And it's called specific heat. If you want to read about it, it will help us cover it in, say, 30 minutes, and then we'll be done. It does have a lot of problems, though, math conversion, so I don't want to rush through it. It will take me another 30 minutes, and you know, I didn't.
At the end of the homework is kind of all these like math questions.
Yes.
I didn't do that part yet.
Right, don't do it then.
Okay.
And I'm going to move the deadline.
I started half of it, but
Yes. Good thinking.
I know, I was like, I didn't learn this yet.
Yeah. Okay, any questions? So there's no meeting next week. We'll meet 2 weeks from today. Thank you.
Do you want us to still do the lab, chapter 3 lab,
I'm going to do the same with lab. I'm going to move them accordingly.
the measuring lab?
Yes, the measuring lab. The number 4, I believe.
Should I hold off?
Yeah, well, I mean, you can open it and I can always reset it. If you didn't like what you did and you want to redo it, it's easy for me to reset.
Okay, sounds good.
Yeah, thank you.
Thank you.
Yeah, I don't want you to like walk away from the course for 2 weeks. Keep working on it because you don't want to fall behind. Okay, yucca. Oh, I'm gonna stop this thing now.